This is group 58, recitation 13 discussion.
All right, so this week was recitation 13. It's about angular momentum again. I thought this recitation was really hard. What about you guys?
Yeah, it was pretty difficult compared to the last one for sure.
Yeah, I think I came up with some good answers. So I guess the first problem, it's talking about a water well with a bucket on a rope that's attached to a cylindrical windlass. And so the handle's removed to allow the bucket to descend from rest, the top of the well to the bottom. And then it gives us the mass of the bucket, the radius, moment of inertia of the windlass, and such and so forth. And then it asks us various questions. So part one, it's asking us to apply the momentum principle to the windlass row bucket system and use the resulting equation to find the bucket's acceleration as it descends into the well. So I just use that similar to how like the net force is equal to the mass times the acceleration. The net torque is the mass times the acceleration times r. And then I basically use the angular momentum principle to set it equal to these various factors here. And so you set I times d omega over dt plus rm dv over dt equal to negative mgr, because we know that dl over dt is equal to torque net. And then if you just set I over r, or if you divide I by r, then that turns this omega factor into velocity. And then you can combine like terms and solve everything out. So where dv over dt is equal to negative mgr over I over r plus rm, which is negative g over 1 plus I mr squared. Did you guys get that?
Yeah, I think so.
Okay. And then part two, ask us to apply the energy principle to the same system and find the bucket's speed before it touches the water surface distance h. So this is just the simple energy principle that the initial potential will be equal to the final kinetic, because we're assuming that as it falls a distance h, all of that potential energy is going to be converted to kinetic. So you just set mgh equal to the kinetic energy of the bucket plus the kinetic energy of the rotating windlass. And then same thing again, combine like terms, factor everything out, solve for v, and then you find that it is equal to root 2gh over 1 plus I over r squared. Did you guys get that?
Yeah.
Okay.
Yep.
And then part three, it asks us to use the system part one to determine the tension in the rope as it's moving down. So I just said that F net is equal to mass times acceleration. And so we know that the net force is the torque, or the tension force minus mg. So I just set that equal to m times the acceleration we solve for at the top. And then if you add this mg, combine terms, such and such alike, you solve the tension to be equal to mg over 1 plus mr squared over I. So you guys get that? Okay. So that was it for problem one. And then I was kind of hoping problem two would be easier, but it really wasn't.
Wait, that question was on the homework, or the homework that's due tonight?
Yeah,
actually.
I know. And it was in our lecture, which honestly, that's where I got a lot of this like information from, because I don't really know how to do this myself, but here we go. So part one, this one I did know how to do myself. It's just asking what's the final angular momentum of the stick and bullet about point A just after the collision. This is pretty simple. L is equal to the momentum dotted with the perpendicular radius. And in this case, R perpendicular is just equal to the length of the stick. So we can just plug in the variables it gives us at the top to find that L is equal to 3.193. Did you guys get that?
Yeah.
And then this one's asking about what is the angular speed of the stick with the bullet embedded in it after the collision. So this is kind of like where so we can say that the momentum is going to be equal to the moment of inertia of the stick plus the bullet times omega final. And then we can set that equal to this momentum because we know that there's a conservation of momentum, I guess is what I'm trying to get at. So if you solve for the moment of inertia of the stick, you get 1/3 m big M L squared plus the little m L squared, which is for the bullet at the end of the stick. And then if you plug in all the variables, divide everything out, you find that omega final is equal to 0.0553 radians per second. Did you guys get that?
Yeah.
Okay. Then it's asking what's the torque exerted by the bullet on the stick if the impact time which the bullet comes to rest is 0.01 seconds. So for this one, I just said that I omega final is equal to I omega initial plus torque net delta T. And so we know that the initial angular, like rotational angular momentum is 0. So we can just set the 3.193 equal to the torque times this delta T 0.01 seconds. And we find that the torque net is 319.4 Newton meters. You guys get that?
Yeah.
Okay. And then change the kinetic energy. This is similar to like energy principle problems we've done in the past. It's just a lot more involved. So delta K is obviously K final minus K initial. And so we know K final is going to be the sum of all the kinetic energies of the stick. So you're going to have the kinetic energy of the bullet, the kinetic energy of the stick's center of mass, so like the K trans, plus the K rotational. So I basically just substitute all these factors in, find that this final kinetic energy is really small. It's 0.0883 joules. And then the initial kinetic is just the bullet because that's the only thing moving before it hits. And then you just subtract them and find that delta K is negative 52.96 joules. Did you guys get that?
Yep.
And then for the theta max, I use the energy principle to solve it. So delta K is equal to negative delta U. So similar to before, you just see that K is equal to this 1/2 times the I omega squared. And then you set it equal to the potential energy after it stopped moving, which would be MGL 1 minus cos theta plus MGL over 2 1 minus cos theta. And then just do a little bit of algebra, rearrange some things, and you see that theta is 1.45 degrees. And then I think that is everything for this week. You guys get something close to this?
Yeah.
Yeah.
Cool. But yeah, that was
Alright.
what I have for recitation. So
Sounds good.
Nice.